Good morning, everyone, and welcome to session 2. I'm Carly Pittman, a civil engineer here in our Edmonton office, and I'll be moderating this session. So our theme for this session is making decisions, which is a part of our everyday lives. Our first presentation is on the City of Winnipeg, Baltimore Forcemain replacement project, and our presenter is Jason Lueke. Jason has over 20 years of experience in consulting, construction, education, and research, focused especially on trenchless engineering and construction. Prior to rejoining AE in 2012, he served as an assistant professor and senior sustainability scientist at Arizona State University. His current role of national practice leader for trenchless technology at Associate Engineering, he provides technical and general engineering support across Canada for all AE offices and coordinates trenchless practice at Associated, including design, inspection, and construction standards. Fun fact about Jason is you may or may not have guessed, but he is an avid Scouts Canada leader. So on that note, please, Jason, take it away.
Excellent. Thank you very much, Carly. Good morning, good afternoon to some of us. Thank you very much for being here today. The theme of the next two presentations, we're going to be talking about decision making, and both of them kind of focus on a lot of you out there are familiar with what we do in terms of decision support and using multivariate criteria type decision process making. And this one here about the Baltimore Forcemain kind of focuses and discusses some of our traditional kind of decision making applications. And then Connor Wilson is going to be talking about a decision-making process that was developed using the same kind of process, but applying the GIS to it. So it was more of a spatial decision-making. So that's these two presentations go nicely together, and they serve very different purposes. This one here is we're looking at alternatives for crossing a river or for fixing an existing force main on a bridge, where Connor is going to be talking about a project where we had a large land area. We had to choose some locations, put some shafts in. So was it very, the spatial decision making was very applicable in that situation. Connor will explain all that. So anyways, we'll get going here. So this project here, and a good shout out to our City of Winnipeg people for joining us today. Thank you very much. We're talking about the Baltimore Forcemain crossing. And I entitled this, When Trenchless Became Not Trenchless, because essentially as we go through the decision process, it kind of led us down a path where it kind of made sense, and all of a sudden we get to the end and it didn't work out. And so we'll explain that. All right, so in terms of the outline of the presentation today, we'll go through a little bit of background on the Baltimore Forcemain. We'll talk about the Forcemain River concept study, where essentially we kind of went through their traditional decision approach. And then we started doing the concept validation, because it went through, and generally we have one or two that looked like a preferable options. And in order to kind of go and take it to the next level, we got to do that concept validation to make sure that what we're suggesting is appropriate. Then we'll get some conclusions and recommendations after that. All right, so some background. But here's just an aerial view. We have the we have the St. Vital Bridge here in Winnipeg. This is the Red River. And the force main itself was a 500 diameter steel pipe, and it was actually suspended underneath the northbound bridge deck here, going across the Red River. And it was built in 1988, approximately 200 meters in length. The configuration itself was a steel pipe. It was inside an insulated carrier, and then it was suspended under the bridge. So late in summer 2018, the city was alerted. I believe the story was related to a kayaker going down the river that noticed that there was water leaking from this pipe. And during that summer, the Forcemain experienced three leaks, and the city had to go in and do some repair clamps. The authorities were notified. Everything was put in place, and then the city went through and started a program to actually investigate how big this problem was. And they did the ultrasonic thickness testing, and determined that it was very thin. And it was kind of a unique kind of situation in that it was the invert of this pipe was very, very thin. The top and the bottom was relatively almost intact, almost original size or thickness, but it was just the bottom, the invert, which was kind of really causing some troubles. So here's just kind of again just kind of looking at with the rest of the system in place. So we have the Baltimore lift station up here in the north, it would pump through a 1.5 kilometer force main to get to the actual St. Vital Bridge crossing. There's where we had the actual Baltimore force main crossing itself, and then it would again go by gravity or a force main kind of gravity back up here to the Major lift station, and then it would be pumped into this dash line to get into the rest of the system. So when we're taking a look and developing options to replace this, some of the things that kind of came up is that, well, we noticed that we have this lift station up here in the north. We're actually pumping just over here, but in the end, we got an extra 3 kilometers of pipe that takes us over to the Baltimore force main crossing. So it's, these kind of things came into play, and we're looking at different options. Like, can we short circuit this and just directly deliver from Baltimore to the Major lift station and avoid 3 kilometers of this force main? So we're going to move in and start talking here about some of the different options. And I'm kind of fast tracking some of the front end stuff because the back end stuff was much more exciting in terms of the concept design. So how to do the concepts we looked at was we looked at various options. So one, and this is part of the decision-making process, is we develop these options, take them up to a concept level of design, put together a description how it works, pros, cons, and then put together a cost estimate so that we can actually make some decisions or help us to make our decisions. So the first option is relining with cured in place pipe. So to just take the initial, the existing pipe and just put a liner through it. Slip lining, putting a structural or a flexible liner through this. Replace in kind, so essentially taking it off and just putting exactly back the same was. And all these things had on the piers, there was some cradles for the pipe. They would have to be replaced. Option 4A and 4B is microtunneling. 4A was, if I'm going to go back here really quick, the A's, the alignments were doing the alignments closer to the bridge. And the B alignments are trying to do the short circuit going from the one lift station to the next. So that's where that A and B option comes into play. So we had A and B options for microtunneling and directional drilling, and then we had the weighted pipe option, which was essentially to put a weighted pipe, high density polyethylene, across the river to convey the flows. So now we kind of get in and we've skipped a whole bunch of steps, but in that whole process, we developed some evaluation criteria, and this we put together specific to the project, working with stakeholders and the owner, and we developed some of these ideas or some of these criteria which we want to evaluate the different options against each other. We take the evaluation criteria and we do what was called a pairwise comparison, and we rank those to each other. We compare each one to each other to determine which one is more important, and we say how much more important those things are. And that leads us to developing a weighting. And you can see here that we get a weighting for these different criteria. And in this case here, with the stakeholders and for the purpose of this project, operation, maintenance, performance, and certainty was one of the highest weighted criteria when it comes to making a decision. Things like the social impact, infrastructure security, schedule were lower. It's not that we didn't care about them, it's just that in the relation to making a decision, the group felt that these other criteria were more important and had more weight on the overall decision-making process. So then we have on top here, we have our different options. So we have quite a few of those, and we go through as a group and we take a look and we compare. So in terms of environmental impact, which option would have the least environmental impact? And so we give that a high score, 10. And then we come back and we compare each of the other options to our initial high score to determine how they relatively are comparable in terms of that criteria that we're evaluating. In the end, what we get is if we do a sum product where we multiply the weighting by the score that's given, we get what's down here in the bottom. We get the total criteria score, right? And in general, if we add that up, the one that has the highest criteria score would be the one we preferred to take forward into preliminary design, detail design for the project. And so here we see that microtunneling option 4B and HDD option 5B were the highest rated criteria options based on the criteria and process we went through. So those are the options that were short-circuiting the installation. So we go through and now we do what we call a value ratio, and we take the estimated cost, the capital cost of that construction, and we take the total weighted score divided by the estimated cost, and we get what the value ratio is here. And you can see here that from the flexible liner comes out 233, and so the higher the number, the better. So right away we take a look and we see some issues here is that the ones which came up as being some of the highest ranked in terms of options aren't even close when it comes to value ratio. So it kind of gives a little bit of a contradiction. So we need to go in and do a little more additional investigation. So here we can see the options on the left. We have the total score ranking from the criteria. So that's just a numerical ranking. Microtunneling 4B had the highest score. And then in the value ratio ranking, the flexible liner had the highest score. And you can see that we have this this discrepancy that none of our options actually line up in terms of what's great from a criteria perspective, but didn't really so much work in terms of the value ratio perspective. So it's like, well, geez, what's going on here? And it doesn't always happen, but it requires you to do some thinking then to make sure we're making the right decision. And then what comes into play is that, each of these options are a little bit different. Some of the short circuiting options had a definite impact in terms of the long-term operation maintenance costs. Because if we're short circuiting and we don't have 3 kilometers of Forcemain, that definitely changes how those pumps are going to act and the maintenance and all the activities required by the city to keep the system working. So we go through and we looked at the total life cycle costs, because some of them, they're not all equal. Some would be a short-term solution, may only have a 10, 20-year design life and we'd have to do something again. Others, like the drilling, had 50, 75-year design life. So there's various differences in terms of design life and then also operational maintenance. So we go through, and you were at the city, Cynthia there from the city, and we use a net present value template to the 35-year assessment. And then we come up and we figure out now that we do the net value assessment, and it now starts to make sense. And again, we have then we have the directional drilling coming in as being the preferred. Option 5A is being at the more or less parallel to the bridge, off option 5B being over closer to lift stations. And then it became clear that the next best was the replacing kind. All right, so we're still moving forward now, thinking we're doing directional drilling. So things are going great. Now we start doing the concept validation. So we reviewed options 5A and 5B, and we looked at option 5B initially because option 5B seemed to have the greatest benefit from operational maintenance perspective as we're short-circuiting it. Option 5B was about 540 meters in length, had a little bit of a complex geometry, which I'll show you right away. And then we had some concerns about the geometry. There's one thing to put things on paper, and that looks kind of nice. City, Winnipeg has some interesting geotechnical, geological features in terms of we have the overburdened material over top of bedrock. So that does cause some issues there. And the bore path that we proposed was fairly complex in terms of both horizontal and vertical curves. And so we brought in a contractor and to help us kind of do a constructability review to make sure we weren't crazy moving forward. Option 5A was much more traditional in terms of a straight profile, and it was just under 400 meters in length. So here's option 5B over here on the right-hand side. Hopefully you can see my mouse moving. On the north side on the top side of this picture, you can see the major lift station. Sorry. Oh, I missed. There's a lift station up here, and then we come down to the major lift station down here on the left-hand side. And so the entry here, and complicating this also, was the slope stability. There's a lot of erosion occurring here and instability in these banks along the Red River, and it kind of forces us to put our bore path in a location that's not going to be impacted by the slope stability. So we couldn't do a traditional kind of straight across. We had to almost kind of come in parallel on the entry and then start doing our curves underneath the slope stability. Hopefully, and by this time, we were going to be in bedrock so that we can do all our steering within the bedrock. And if we knew we're in a bedrock, we'd be out of that slope instability area. So that's where you get these little bit of, you got the horizontal curve, the vertical curve occurring at the same time, and just trying to avoid that slope stability. So this was, this was option 5B, and we're going through to do the feasibility of this. Option 5A was much more traditional. There's nice working space on either side in these green spaces kind of thing, and that allowed us to do just a straight shot going across, just under 400 meters. So we go out, do the site reconnaissance, we do the riverbank stability, identify locations for geotechnical investigations. So essentially, and I guess I missed one point here, is that when we got into option 5B and started looking at the workspace and we started looking at the constructability, we didn't get good reviews from the drilling contractor. And so that kind of forced us, I guess, or really to consider that if the contractors are not saying this is feasible, we can't take that design. And really what the feasibility comes down to is trying to make those complex steering arrangements within the bedrock. And they were concerned that they just wouldn't be able to make some of those things work. And that was before we had geotech even. So we kind of knew from other work we've done in Winnipeg. We've done another crossing further down by Chief Pegasus, the bridge there. So we the Kildonan Forcemain crossing. So we knew the geology there, and we kind of understood that the bedrock was kind of complex. So then we said, okay, well, option 5B is off the table. Let's go to option 5A now. And so we focused our geotech on option 5A. So we got 2 boreholes, 46 meters in depth. We had the profile already set up so we can tell the geotech to get down to their appropriate depth. Samples were taken to determine the relative strength, the gradation, the plasticity, and the abrasivity. And those are things which are important from a contractor's perspective so they can understand what tooling they're going to need. So it's very important, we're not doing a geotechnical baseline report here, but at least we're getting some information to the contractor so they can size up some of their tooling they need. Oh, soil stratigraphy, no surprise here. Clay, silty clay, silt, sands, gravel, bedrock. Trek Geotechnical, local there to Winnipeg, did the report. One of the things that kind of came up here, though, is that the subconsultant that did the drilling, we had conversations with them, and the words, never seen this formation before in Winnipeg, the most difficult drilling we've ever encountered in Winnipeg, raised a few alarm bells, right? And it really came down to is that there's in this location, there's a fairly unique formation. And what it was alternating between very competent hard material and very soft rubble material. And the issue here is that from a steering perspective, even if you're trying to get down, if you're skirting across these hard layers, you're going to extend. You won't have the steering response you're expecting. And then you get in these soft rubble layers, and all of a sudden now you've got circulation issues. You can't maintain the circulation inside your borehole. And everything was hydraulically connected. There could be potential for some frac outs. And then again, they had significant difficulty drilling the boreholes. Here's just a cross-section of the area here. Here's the inferred bedrock contact layer. And you kind of see, you got the clays, you got the tills, and it was this layer here. And realistically, I'm not sure if the geotechnical report, if we would have looked at the geotechnical report on its own, without talking to the driller, I'm not sure if we would have got the same, we would have interpreted the same way. And so, as a lesson learned from us, I'd say is that it was important to talk to the driller that was actually doing that work to get that hands-on kind of experience and understanding of what the ground was doing. So that was a real lesson learned there, that the benefit of actually talking to the geotechnical consultant in this case really led us to understand what the difficulty was and what the concern was moving forward on this installation. All right. So here's some of the cores. So again, we went through, and the cores, the boreholes were determined based on doing the preliminary geometry on the bore path. And that's one thing that, I think is really important, that if you're working with a geotechnical consultant and before you do your drilling program, is you should have a preliminary drill path already designed. So at least you have an understanding in terms of what depths you're going to be at. And then we can help the geotechnical consultant plan their boreholes so that we have the right information at the right locations. One of the things that really causes us a lot of problems sometimes is not getting geotech at a sufficient depth. And it happens where, it happens to us all the time. We have an open cut project where we need to make a quick change and move over to do it by trenchless. And we get in a situation where the geotechnical information we collected for the open trench type operation is not deep enough or doesn't have the applicable parameters that would use from a directional drilling design perspective, or to give the contractor to have the right information to plan their installations. And so that's where, working with Trek, we determined what that bore path was and said, we need these boreholes being 46 meters deep. I think it was even maybe a little bit deeper, because I think we're drilling at maybe 30 meters deep. And this gives us an opportunity to get to know what that ground is below the proposed bore path. Why is this important? Is that part of the directional drilling design component is we go through and we determine some pipe loading. We put a preliminary bore path together. We do a hydrofracture analysis. And so that's nice. But when you're vetting or proofing that design, you have to take a look at what the geotech is telling you. And we want to avoid things which are going to be showstoppers for directional drilling. So in particular, cobbles and gravel layers. Those are things we want to avoid. And so once the design is complete, you do have to proof it and vet that if whatever stratigraphy you're in, based on the geotech, is still applicable and is still good for drilling. And in this case, it's one thing to go at an angle through an unpopular, let's say, or a layer that's not all that technically feasible for drilling in. It's another thing to start going horizontal through that. If you're continuously going through, you have concerns about things caving in. You have concerns about boreholes, fluid leaving the borehole. In this case here, another concern would have been potentially if this rubble and loose portions in the river are hydraulically connected to the river itself, we'd have potential issues of water passing through a borehole, and it wouldn't work as well because you'd be basically flushing out your bentonite. You wouldn't be able to get a nice filter cake and keep the borehole stable. So really important, you can see here, you can see the rubble that, whoops, sorry about that. You can see here the rubble that we'd be going through. And this would be definitely an issue in terms of borehole stability and keeping circulation within the borehole. Other areas, you can see like looking here, these cores are nice and solid. It's great to be drilling through. But this rubble was definitely a problem. And there might be some, drilling in rubble and cobble. From a drilling perspective, we want to get into a layer which is going to be as homogeneous as possible. And so going into the bedrock is definitely a preferred location to be in, as opposed to being in tills. Tills, you have cobbles, gravels, and stuff like that, which are going to get in the way. But if we can get into something which we have a predictable behavior, that makes drilling and the design so much easier, right? All right. So, subsurface investigation. Might be just summarize some of these things again. So, concerns of the formation. So, I talked about loss of circulation. So, just in terms of the amount of fractures, we may have issues in trying to keep the borehole full of fluid. And the circulation, again, it's not because of frack out. It's just because we want to make sure that we have circulation. If we have circulation, we can keep flushing the cuttings out of the hole. So that's where that loss of circulation comment comes in. Difficulties in steering, we talked about that. The alternating hard and soft layers, and then the borehole stability. So, at the end of that, unfortunately, we had to conclude that, there was a high risk of drilling this in terms of, potential claims from the contractor, losing tooling down hole, and then just even the installation failure. So we actually had to recommend against directional drilling. And so this is where, unfortunately, it became a non-trenchless project. So we did have some geophysical survey that was going to be on order. But really, once we did the boreholes, we came to the conclusion that based on what we saw there probably wasn't any real reason to do the geophysical. It wasn't going to tell us anything more. And in particular, in terms of the way the layers were set up, geophysical is great to identify kind of those massive or significant changes between soil consistency. So if we have these alternating layers of hard and soft, I don't know if it would have really defined anything more than we knew from the boreholes. So then that's another, maybe another lesson learned here is about that staged approach to doing geotechnical investigation is really taking the geotech, analyzing it, and then making a choice moving forward in terms of if we need more geotech or a different thing like geophysical. So conclusions, recommendations. So we revisit the net present, and in the end, when option 5A and 5B didn't turn out, the next best was a replacing kind. And, City of Winnipeg, I believe this is the option that they're pursuing right now. And, it's been a while. The City of Winnipeg had to set up an emergency kind of bypass or temporary bypass type situation over top of the bridge. So they've been, unfortunately, kind of moving sewage to the Forcemain on the bridge for at least a year and a bit at this stage. The benefit of having that there is that once the replacing kind is moving forward, at least that bypass is in place, and it one less thing for the contractor to worry about. So that is underway, I believe. And I'm sorry, I didn't check on the status of it actually. All right, so conclusion recommendations: abandon HD crossing at the option 5, proceed with option 3, replacing kind. Acknowledgements: City Winnipeg, Bronwyn Jones, Cass Zurich, Stacy Cornier. And from Associated, Colin McKinnon, who's our project manager, Chris Lamont helping with the drilling, and Linda Chaco was also involved in the drill design and analysis in terms of the decision support. And that's it. Thank you very much. Carly, over to you.
Thank you, Jason. So we only had one question, and I think you already answered it. It was if there were considerations for to drill geotech from within the river. So I think you did answer that one already.
I could comment some more.
Sure.
Perfect. Craig, that's
Sure.
an excellent question. And this is another one of the lessons learned that, I think is important to discuss. And we discussed a bit of it yesterday, was the idea here that, from any kind of trenchless, be it microtunneling, directional drilling, we need to have sufficient information. And having boreholes simply on either side of the bank is probably not sufficient for a majority of crossings that we're involved with, especially when we're talking 300-400 meters in length. Because now we're kind of drilling blind, we're designing blind. We don't have the information in the river. So, I think it's really important to try to get geotech within the river. And, there are some concerns with bringing a rig out there and some timing issues. And that's where I think the geophysical is a good alternate or a good supplementary piece of information to the boreholes on the side of the banks. So, I think it's getting the geology within the river is really important, if at all possible.
Okay, and we actually do have one more question, Jason, and that's Jason, how did you come up with the weightings for the different methods?
Okay, so Doug, there's a couple thoughts there. If you're talking about the weightings for the different criteria, we come up with the weightings on the criteria using what we call a pairwise comparison. It's basically matrix mathematics where we put in on the vertical axis, we put in all the different options, the same, or all the criteria. On the horizontal axis, we put the same criteria. And then your facilitator goes through and he says, okay, facilitator being me in this case, the facilitator then compares, well, how's our environmental impact compared to constructability? And as a group, we come up with and we determine which one of those is more important, right? And we compare each one to each other. So you basically fill out a matrix on the upper kind of half of that matrix and in comparison which is more important to each other. And then additionally, we add in another variable, which is like, well, how much more important? Is we just marginally more important or significantly more important? And by using that in a combination of which one's more important, in addition to the weighting, you go through the matrix kind of does some cross multiplication, and at the end it kind of gives you that weighting in terms of those criteria. And the beauty of doing that process is that as we're doing it, we're documenting that decision making, we're documenting the discussion, such that for our clients, if they're going to go through now and going to go talk to their management, they have a document that kind of outlines how the decision came to. And it's a repeatable kind of structured approach to making that decision. We take that weighting, compare it to each of the options, and then again through discussion, determine which option is most favorable or most beneficial when comparing that particular criteria. And again, it's all documented, put into a formalized approach that we're not using gut feeling here. We're doing a structured decision making, and that really helps, in my opinion, to talk about these things and to prove or to illustrate to others who may not be involved with the decision making process how we got to that final decision.
Perfect. Well, thank you, Jason. That was a great case study on the importance of decision making in the early stages of a project to set it up for success.
Excellent. Thanks, Carly.
Okay. So we'll hand over to our next presentation. So as Jason hinted earlier, our second presentation is on the Cambie Richmond Tunnel Alignment GIS Spatial Analysis Project, which will be presented by Connor Wilson out of our Vancouver office. Connor is a mechanical engineer with over 7 years' experience in design of regional water and wastewater infrastructure. He received his Master's of Applied Science in Civil Engineering from the University of British Columbia. In the past 5 years with Associated, he has maintained active design and construction roles in Metro Vancouver's water reservoir capacity expansion program, as well as several large diameter water supply main projects. Recently, he has applied his skill set to shaft valve chamber site selection for the proposed Cambie Richmond water supply tunnel. A fun fact about Connor is that he has a weekly routine that involves karaoke on Friday nights, which has been interrupted recently, but he is excited to get back in his groove someday. So Connor, please take it away.
That's right. Thanks very much, Carly. Appreciate the intro, and welcome all. And thanks for joining me and well, the opportunity to present on behalf of our team here. So I've been designing water supply infrastructure in Metro Vancouver for several years now, but I'm normally called in at the detailed design stage and getting involved at the ground level for the Cambie Richmond water supply tunnel. I mean, it's really demonstrated to me the power of GIS for decision support. So I hope I can convey some enthusiasm for the approach we've adopted here. And I'll give you a view of the early stages of conceptual design, starting with background and scope, conceptual design objectives, go through the spatial decision criteria. I'm going to roll out some of the multi-criteria spatial analysis figures, the results of these analyses, and our next steps. So the Cambie Richmond tunnel, it's intended to be an extension of an already well-established water supply network. I mean, this corridor has been an important artery for transmission mains since at least the 1950s. And mains from the north, they're conveying water from the Seymour and Capilano watersheds to South Vancouver and through to the cities of Richmond and Delta via these existing Fraser River crossings. Now, as you'd expect, these areas are rapidly urbanizing with Canada Line SkyTrain stations on both sides of the river. So careful water planning has been undertaken to project demands out to year 2121, and these existing crossings they present a bottleneck in the near future. And existing infrastructure is aging. Of course, seismic resilience is a concern, and these are to be designed for a 100-year horizon and to modern seismic criteria. So within this black boundary here is the predefined data collection area. I mean, in this area, somehow we need to identify preferable sites for 2 tunnel shafts, one on either side of the river. The tunnel is likely to contain either a 2100 millimeter transmission main or 2 parallel 1500 millimeter mains. We need to pair these sites appropriately to align a tunnel between them with a minimum curvature radius of 300 meters. The 2 shaft sites are expected to be quite large, not only to locate valve chamber structures, but also to accommodate construction laydown for the TBM launching equipment. And at the end of the day, large diameter open cut water mains need to be established to tie in the tunnel into the existing supply and outfeed. So the primary undertaking for evaluation of shaft site locations is, it's no simple task for a 630 hectare study area extending across 2 municipal jurisdictions. To begin with, we compiled decision inputs from regional and municipal geospatial models, the majority of which is readily available free data. We integrated situational, geotechnical, and constructability considerations into our multi-criteria spatial model. This data provided the high-level view, but the real objective was to strategically overlay and manipulate these models to focus in on kind of a long list of suitable sites. And alongside reconnaissance observations, we collaborated with Metro Vancouver and our technical leads to shortlist 3 shaft sites on the Vancouver end and 2 sites on the Richmond side. And to further demonstrate their suitability, we developed conceptual plans and profiles for 4 potential tunnel alignments. So starting with the obvious one, we require adequate real estate for the shaft infrastructure, as well as construction laydown and access. We targeted industrial and commercially zoned areas to mitigate construction impacts on residential areas and also to allow for use of well-established haul routes. We aim to optimize capital expenditure by minimizing tunnel length as well as length of open cut tie-ins. And from a geotechnical perspective, we endeavor to find firm ground to embed these shafts. As you'd expect, shaft installations near the Fraser River will be affected by a significant degree by soft soils, and we target sites with shallower liquefiable layers to limit dynamic effects during an earthquake. So let's roll out some of the spatial data layers we use to illustrate these criteria. You'll notice on all of these maps, we show the Cambie, Richmond, and Lulu Island delta mains in blue as a visual indicator of really the tunnel supply source and destination. And note that this transmission main generally aligns with the Oak Street Bridge. And in purple, we indicate the alignment of the Canada Line SkyTrain. These are shown common to each layer because in the end, we want to avoid threading a tunnel between the piers of the bridges. So first up here is land use. In red, we illustrate residential zone parcels, as well as road and rail rights of way. What is left is commercial and industrial zoned land, shown in light and dark green, respectively. And these colors, they actually represent a value with industrial space scoring a bit higher than commercial, which I'll elaborate on in the coming slides. So at this point, it was prudent to consider registered sites with social, environmental, and archaeological relevance. We use this layer to make designers aware of things like heritage sites, schools, care facilities. We also masked off the riparian offset for the Fraser River. And on the left in turquoise, we've identified a registered archaeological site. So logically, we developed a no-go mask for areas we want to steer clear of. To this mask, we added the frequent transit development areas on the north near the Marine Drive SkyTrain station, as well as the TransLink operation and maintenance facility on the Richmond side. And this layer certainly made it clear how congested these pre-developed areas are becoming. The challenge became even more evident during reconnaissance, as we found well-established industries and stratas have been replaced with new commercial developments like car dealerships and self-storage facilities and the like. So with the mask now laying out some more boundaries, we could begin the constructability conversation. With help from McMillan Jacobs, we define the spatial requirements for construction of shaft infrastructure. So we need at least 8,000 square meters for the TBM launch shaft, construction laydown, as well as muck disposal. And on the other side, we are looking for a minimum of 4,000 square meters for the TBM retrieval shaft. Although we know boring uphill is preferable, at this point, we don't know whether we are tunneling from south to north or vice versa. So to illustrate favorable parcels, we created this layer with purple outlining parcels suitable in size for retrieval shafts, and the hatched parcels suitable for either a launch or retrieval shaft. So the product of the situational analysis was this shaft site long list. Now we have identified 61 suitable sites. How do we distinguish between them and shortlist 5? At this juncture, we're thinking ahead. We're visualizing tunnel alignments. And as you can see, the Oak Street and SkyTrain bridges, they revealed clearly defined boundaries, which eventually became the basis for these shaft zones. Only a few zone combinations make sense if we are trying to avoid tunneling beneath existing structural crossings. So the strategy from this point forward was to score sites within the same zone against each other to arrive at a top candidate for each zone. So we thought, well, why not get the multi-criteria model to score them for us? So the obvious spatial model outputs will relate to length of tunnel infrastructure. And this would include the length for open cut water mains to tie in the shafts to the existing water supply. We developed spatial bands around the Cambie, Richmond, and Lulu Island delta mains. And each band is assigned a score, ascending with proximity. For instance, a shaft site located closest to the supply is assigned a higher band value, and is shown in the green areas. Next up is tunnel length. And given that we were trying to align a tunnel between shaft zones that are directly across the river from each other, we generalize that shaft sites located closest to the river will result in the shortest tunnel length. Again here, shaft sites located in the green band are assigned a higher value. Which brings us to our first multi-criteria layer. This is the combined situational analysis. I mean, rather than reporting spatial values in a massive spreadsheet and strain the eyes of our collaborators and clients, we document these results of the analysis visually. And what we've done here is manipulated the value outputs from the land use, proximity to tie-in, and tunnel length layers, and we've assigned weights to each of them based on agreed upon design relevance. You can see some clearly defined favorable areas beginning to arise here, especially near the river shore and along the existing transmission line. But using the situational layer alone might wind up locating shafts in areas with suboptimal geotechnical conditions. So we turn to our geotechnical lead, Golder, to help steer the ship. And within the study area, we were able to pull geological data from a fair number of existing boreholes. Golder used Leapfrog software to develop spatial geotechnical models. And as I understand it, this software essentially interpolates between boreholes to efficiently trend geological conditions across the study area. So one of the most important geotechnical considerations is the liquefiable layer thickness. This includes soft soils such as river sands and marine sediments that are subject to lateral displacement in the event of an earthquake. If this liquefiable layer is exceptionally thick at the shaft site, well, the shaft needs to be designed with enhanced capacity to overcome lateral pressures. And as you can see, there's some problematic areas in the northeast corner in Zone 1, as well as deeper pockets within Zone 4 and 5 on the Richmond side. I mean, similarly to the situational layers, these contours represent a severity value with red areas assigned lower scores. Now, depth to glacial till is a parameter that our tunnel and shaft design lead is particularly interested in. They want to know how deep the shafts will be and how deep they'll need to be installed in order to embed them in firm ground. The green band indicates depth to till greater than 40 meters below sea level, while red indicates till at less than 80 meters below sea level. So that's quite an aggressive grade to this deposit from north to south. Lastly, for our geotechnical layers, we spatially approximated the severity of lateral displacement. Illustrated here, the bands in red, I mean, they're displacements of greater than 3 meters. In yellow, it's between 2 to 3 meters. And in green, that's less than 2 meters. So as we did for the situational layers, we stitched together a composite layer illustrating shaft site location values from a purely geotechnical perspective. Lateral effects become especially problematic in areas with thick liquefiable layers and within bands with high lateral displacements. So we compounded these two parameters. And then with the input from our collaborators, we weighed the geotechnical analysis values 50-50 between lateral effects and depth to glacial till. This revealed some areas in green and yellow where lateral effects may be balanced to some degree by relatively shallow glacial till. Which leads us to our coveted heat map. This figure essentially records the overall results for our spatial analysis all in one place. It integrates the composite maps for situational and geotechnical analyses and blends them to illustrate spatially the full range of design criteria. And we've assigned a 40% weight to the values from the situational composite analysis, which, as discussed, includes land use, tie-in proximity, and tunnel length. And the values output from the geotechnical composite analysis from the previous slide are assigned a 60% weight. Here you can see the balancing effect that alignment and tie-in interconnection length has on geotechnical outputs as some green arises where it would have been considered yellow from a geotechnical perspective. And we use this heat map as kind of the primary tool to collaboratively score and rank shaft sites within each of the shaft zones. So results and next steps. So why go through the trouble of creating composite maps for site selection? Well, the real value comes from multidiscipline collaboration. And with these visual cues, we curb the tunnel vision you might experience if you're simply focused on satisfying discipline-specific design criteria. And to the team, you can more effectively communicate why you prefer particular shaft sites. And our goal here was to provide shaft site options. In the end, it's up to the client to select which ones. And these spatial figures, they provide a documented roadmap on how we arrived at these options. I mean, these tools are essentially created to streamline the process of secondary screening, where we shortlist 5 out of 61 sites. We later had help from Metro Vancouver property specialists to weed out parcels that might be difficult to acquire. And later, through our site reconnaissance efforts, we visited most of the sites to see what was actually there. And in some cases, revealing that a parcel is now empty or redeveloped, or a railway spur has been abandoned. Now, with the high-level composite maps and the secondary screening results in hand, we're able to hold a multidisciplinary workshop and agree upon the actual site selections. And between these options, we identified 4 possible tunnel alignments. All of this before developing any drawings. And now we're ready to develop the tunnel profiles, which we would traditionally associate with a conceptual design deliverable. For each of the proposed shaft site pairs, we incorporated the geological stratigraphy, and that was spit out by the Leapfrog model. And the crossings were generally envisioned to have a 15-meter diameter launching shaft, an 8-meter diameter receiving shaft, and a 3.8-meter tunnel bored below the river through the glacial till. And again, we've proposed 2 options here for the steel water main piping, either a 2100 millimeter main or 2 parallel 1500 millimeter mains. So here we are, and where to next? Well, we found that the multi-criteria spatial analyses, I mean, they allowed our conceptual design team to execute site evaluations in a highly coordinated manner. The narrative for this process is clearly recorded in our project design report, and the client or those building off of our work, they can pick up this document, retrace our steps, and refer to it as they advise subsequent decisions. So now, advancing into the subsequent tasks for the conceptual design, we have our AE environmental group investigating the selected shaft sites to evaluate environmental or archaeological concerns. We also have a drilling program by our geotechnical lead, which is currently underway at these sites. And this is to verify the geological modeling results that were used for the basis of site selection. And finally, we're moving into the engineering assessment now, where we further develop hydraulic basis for transmission main sizing, shaft and tunnel design concept, and constructability considerations, which in the end will advise our recommendations and cost estimate. So again, thanks very much for the opportunity to speak on behalf of this very skilled team. I'd also like to thank our client reviewers, Jason Warren, Murray Gant, and Frank Huber, as well as Metro Vancouver's property acquisition specialist, Paul Wang. And of course, our technical and administrative project managers, Jason Lueke and Lewis McRae, GIS modeler, Kent Richardson, which did some amazing work here, and our environmental lead, Jennifer Purvey. So I'll open the floor to some questions here. Obviously, I'll allow Jason to chime in for some of them as he was the mastermind for this, multi-criteria methodology. And my contact information is laid out here if you'd like to reach out.
Thank you, Connor.
That was great, Connor. Well done.
Thanks.
So yeah, going through here, maybe just a couple notes, and going back again to the last presentation about, Connor kind of touched on that verification stage. And, we went through and, Connor, in the age we're in with COVID, I mean, a lot of these things we have to do remotely, right? So Connor being local in Vancouver, he got on his motorbike and he trespassed. He went to visit as many of these sites as he could to verify that, just from a space requirement that they were there. And that's the other thing too, is that, McMillan Jacobs are, they're involved as well. And they went out and verified to make sure that, from an access perspective here. And that's also, it's one thing to take that information and kind of use it as a screening tool to kind of decide upon or, kind of narrow down the areas which we think are favorable. It's that in-field vetting which is really essential, and so we did a verification, on-ground verification of information, and now that's where the Golder's involved doing the geotech, and we in the process of obtaining permits and permission to go search or to go do borehole programs on those 5 preferred sites, and we don't know. We have that leapfrog model that's going to kind of give us an idea of what's going on there, but without having these boreholes within where we think are the proposed site locations, that's where we're really going to verify whether or not these 5 sites that we identified are the ones to go with. And so even Connor alluded to as well is that we saw there's different zones. So even right now we don't have. There's a couple zones on the west side of. Connor, Oak Street Bridge.
That's right.
That were eliminated just because there was no space. You have the River Rock Casino there. You have on the south side, the best land was actually Costco. I think it'd be hard to negotiate with Costco to get some land there. But anyways, everything on the west side of the Oakmont Street Bridge, Oak Street Bridge, was definitely an issue that we couldn't work. So we're only working on those. There's only 3 zones. There's 1 on the south in Richmond and 2 in Vancouver. And so we still don't actually know the precise alignment we're going in because we need to verify what the ground is at these locations. And the other thing we're looking for is from a contamination perspective. There's some risk there. So yeah, we got to wait. And realistically, once we verify these things, maybe those sites aren't going to come out, and then we have to go to the next few sites which are preferable and do some additional investigation. So I mean, we're still in that early stages, and geotech hopefully be wrapped up here. I think we've got a couple boreholes already done, and then we're going to be going in to do some additional geotech here over the next few weeks. And again, it's this whole staged approach that get the geotech we need to kind of make the decision at this point, give us more information, and then we can get once we move into preliminary design, that's when we can get a more full-scale geotechnical investigation underway. So if there's no other questions, thanks, Connor.
Thank you, Connor. Thanks, bro. We'll see
Thanks,
you in a bit.
Carly.